Hello, my name is Vardhan and I am going to discuss about my project topic, which is BER analysis of radio receiver equalization algorithm using BPSK signaling. To have an overview of the project, first we will discuss about the introduction and the motivation for equalization, which is basically ISI removal. Secondly, we will go to modeling the equalizer and see how an equalizer works. We'll have a look on equalization classification and the algorithms which are used in equalization. We'll primarily focus on two major equalization algorithms, which are zero forcing algorithm and the MMSE algorithm. We'll try to formulate them using matrix notation, and for the simulation purpose we will use BPSK signals and pass it through an AWGN cum a relay feeding channel. We will use zero forcing for the first part and MMSE for the second part. What we will do is we will use BPSK signal, pass it through an AWGN and relay feeding channel, see its BER performance, and then implement these algorithms and check how better these algorithms behave and which one is better amongst what. And finally, we draw a conclusion by comparing the zero forcing and MMSE algorithms. As we know, wireless channels are hostile, so we need to compensate for the channel impairments. What we have to do? We have to invert what the channel does. And how we have to do? We can do it only when we know about the channel. So we have to know the channel and we have to remove the intersymbol interference. So what is it? Intersymbol interference is a form of distortion of a signal in which one symbol interferes with its subsequent symbols. If you go to this example, if you can see that when a signal passes through a band limited channel, in the time domain, the pulse gets smeared like this, and when it gets smeared, these smeared edges will interact with each other and will blur out this part of symbol. So this is basically an interference in time domain. So mathematically, xi is interfering by using the channel gain, which is not ith but of someone else's. So this part is mathematically denoting the ISI. So what we have to do? We have to mitigate the intersymbol interference, and this intersymbol interference mitigation technique, which is the equalization, has to be adaptive. Why? Because the channel is always changing, so there has to be some kind of adaptive algorithm so that it can mitigate or it can cope up with the channel changes. So how it is different from diversity? Diversity is used to mitigate or reduce the depth and duration of fading, whereas equalization is used to mitigate ISI. This is a simple diagram where it clearly shows that when the output of an equalizer is compared with BK, which is nothing but a type of XK or a replica of the transmitter symbol. So we compare the output of the equalizer with a sample, and if there is any kind of error or if there is any kind of deviation from the actual transmitted signal, there would be an error signal which will update these weight vectors W, which will ultimately adapt the filter coefficient. So basically what happens is equalization is a FIR filter, and these are the filter coefficient or the filter weight which has to be updated every now and then. So this procedure is how an equalizer works. So basically, if you model it as an impulse response, the channel impulse response has to be modeled as a single ft function of time, and yt is an input of the equalizer. Now what happens is the output of the equalizer goes to a decision maker, where this comparing of the standard signal with the input signal is made. If there is an error or if there is some kind of deviation, that deviation is used to adapt the equalizer to the changing channel. So this is mathematically the same thing which I have said. What happens is in the frequency domain, convolution becomes multiplication. So this is the equalizer impulse response in frequency domain. If we take this one on the right side, it would be just the inverse filter, so it goes in line with the definition. This is the classification of various equalizers. So basically we are stressing upon this part, which is the algorithm. Zero forcing algorithms and MMSE algorithms. So basically zero forcing algorithm is exactly what has been said earlier. It is just the inverse filter which undoes what the channel does. But it follows Nyquist criteria. It means that for every other sample other than 2t, it will drive the impulse response or it will drive the pulse to 0. Hence the name zero forcing. Mathematically, y is a vector or is a matrix, h is a matrix, n is a matrix. H is the channel state information, and n is the noise, y is the received symbol. So if we divide the entire equation with h inverse is into y is equal to x plus n by h. Now two things. H should have a valid inverse, and n by h, if h tends to 0, n by h tends to infinity. That means the noise is enhanced infinitely. This is the most negative point in zero forcing. So obviously you get the symbol, but the noise is enhanced. But what MMSE does is, it is better in the sense that it takes the statistical cost function and minimizes it with respect to a weight vector. What happens is, it takes the difference and it tries to minimize the difference, which is the error, which is the cost function. These are the basic matrix definitions which are used in this equation here and here. So basically it is a cross correlation matrix and it is the input covariance matrix. This is basically the error function which has been taken as an expected value, and this function has been taken derivative of with respect to the weight vector and set it to 0. So this is how you evaluate the cost function, or you evaluate the optimal weights. Now BPSK signaling is used for fading channels, and this is how you denote 0 and this is how you denote 1, and the bit error rate performance is given by this. In MATLAB we can use 0.5 times ERF function, which is defined in MATLAB. So if you go to MATLAB, this code, this is the basic simulation of a BPSK signal in AWGN and fading channel. If you simulate it, it will be quite clear that there would be two responses, one AWGN and one relay fading. It is pretty clear that AWGN is quite better performance than relay fading. See, for a given PER, say 10⁻⁻3, relay fading requires a huge amount of SNR. So it is bad. Something has to be done. For zero forcing BPSK, the same thing happens, but what we do is we try to have a channel response and we try to have in several number of taps or several number of filter coefficients in the equalizer. Now if we have more number of equalizer taps, we will have a better performance, which is pretty obvious, but to what extent? To 7. After 7 there won't be much of a SNR requirement improvement, so we should not increase the number of taps beyond 7 because it involves some kind of cost. Now in MMSE, what happens is, in this code, a simple if you simulate this code, you will find two graphs, one MMSE and one zero forcing, which has been plotted on the same figure. This is better to understand just for the sake of comparing. For example, if you take 10⁻⁻2 as a sample BER, you will have only say 1 dB of better performance in MMSE than zero forcing. So why do we use MMSE? MMSE does not does any kind of noise amplification, which zero forcing does. So that is the main drawback of zero forcing. It does noise amplification. So this is basically the simulation results. If you go back to the slide, this has been mentioned, and for the comparative analysis, it is kind of same as the diversity, where we have the law of diminishing return. What it is, if we keep on increasing the number of taps or keep on increasing the number of filter coefficient, the performance will be getting better, but at some point of time the SNR improvement will not be considerably enough. So this is called the law of diminishing returns. So again, the zero forcing amplifier noise and SNR improvement will not be considerable beyond 7 taps. So this is where we should stop using more number of taps. Another thing is that if you increase the size of the steps for any kind of algorithm, the conversion will be faster, but the precision will be lower. So this is where you have to draw a trade-off line. And this is an example of Shannon's capacity, just to show as an example that the theory is the simulation is in line with the theory, that beyond -1.6 dB there won't be much of a performance, like the data rate, or for any kind of coding scheme the channel cannot support more than -1.69 dB capacity. So is MMSE always good? Probably not, because at deep spectral noise the zero forcing will obviously give a breakaway, because it will give an infinitely large amplification, but also MMSE does not perform better. So what do? We use some kind of decision feedback analysis or equalization, which is a non-linear technique. So in conclusion, the filter weight has to be adapted periodically. We have to minimize the mean square error, and which is only possible if we know the channel. We have the proper channel estimation process, and which has several processes like recursive least square algorithm or minimum mean square linear equalizer. So these are basically processes to estimate the channel and to adapt the filters. Thank you.